This introductory slide presents the topic remote sensing for urban resilience, key concepts and frameworks, and situates it within the broader aims of the EPD-Net project. The presentation explains that EPD-Net is an international learning network that promotes ecological planning and design for disaster-resilient and sustainable cities, supported by GIS, remote sensing and artificial intelligence. Remote sensing is highlighted as a core data source for understanding how cities function as complex socio-ecological systems and how they respond to hazards and climate stress. The slide briefly states that the session will focus on the conceptual building blocks needed to correctly interpret remote sensing products used in planning, what remote sensing is, how different sensors and resolutions work, and which indicators are particularly useful for resilience planning. The presentation begins with a concise motivation for why urban resilience has become a central concern for planners and why spatial information plays a crucial role in disaster risk management. It then introduces the basic language of remote sensing, explaining key resolution concepts and the main families of sensors and platforms. The central part of the lecture is devoted to describing concrete remote sensing products that are relevant for resilient and ecologically sound urban planning, including land use and land cover maps, land surface temperature, vegetation indices, digital elevation models, and flood-related indicators. After this, several application examples and best practice case studies are presented to show how these products are used in real planning and design processes. The session concludes with a summary of key messages, a short reflection on limitations and ethics, and a list of references and further readings that students can consult for more technical detail or case study material. This slide shows the learning objectives, which act as a roadmap for what students are expected to know and be able to do after completing the topic. First, students should be able to clearly define remote sensing and describe its distinctive features compared with traditional field surveys or administrative statistics. Second, they should be capable of explaining the main types of resolution, spatial, spectral, temporal and radiometric, and why these characteristics strongly influence the scale and type of urban phenomena that can be analyzed. Third, they should be able to recognize the main sensor types, optical, thermal, radar and lidar, and platforms, satellites, aircraft and unmanned aerial vehicles, commonly used for urban studies. Fourth, students should be able to identify and interpret key remote sensing products that support resilience planning, such as maps of land cover, impervious surfaces, heat island intensity, vegetation condition and topography. Finally, they should understand how these products can be integrated with socio-economic and infrastructural datasets in a GIS to support evidence-based planning, policy design and participatory decision-making aimed at reducing disaster risk and enhancing urban resilience. Here we link the technical topic of remote sensing to the broader policy framework of urban resilience and disaster risk reduction. Urban resilience is described as the capacity of cities to prepare for, absorb, recover from and adapt to shocks and stresses such as floods, heat waves, earthquakes, storms, landslides and slow-onset climate change. Disaster risk is commonly conceptualized as the combination of hazard, exposure and vulnerability, meaning not only whether a dangerous event occurs, but also who and what is located in harm's way and how sensitive or well-prepared those elements are. Cities concentrate population, infrastructure and economic activities in relatively small areas, which makes them particularly vulnerable to cascading failures. Spatial information is therefore indispensable. It is not enough to know that a flood or heat wave will occur. Planners need to know where impacts are likely to be concentrated and which neighborhoods or infrastructures are most at risk. This slide sets the argument that remote sensing, as a systematic provider of spatially explicit information, is a key ingredient of any serious attempt to understand and manage urban resilience. Remote sensing is the acquisition of information about objects or areas at the Earth's surface without direct physical contact, typically by measuring reflected or emitted electromagnetic radiation from sensors mounted on satellites, aircraft or drones. Here we explain how remote sensing differs from traditional fieldwork not only because it is physically distant but also because it enables repeatable, synoptic coverage of large areas, making it possible to monitor changes over time in a consistent way. Imagery captured by sensors are processed into georeferenced raster datasets, which can be analyzed quantitatively to derive thematic products such as land cover classifications or temperature fields. For urban resilience, this means that remote sensing can reveal spatial patterns and temporal trends that would be extremely difficult or expensive to capture with ground surveys alone, such as the evolution of impervious surfaces, the progression of urban heat islands, or the expansion of built-up areas into flood-prone zones. Here we get familiar with the parts of the electromagnetic spectrum most relevant for urban applications. We show that remote sensing instruments operate across different wavelength regions, including visible light, near-infrared, shortwave infrared, thermal infrared and, in the case of radar, microwave frequencies. Each surface material, such as water, vegetation, bare soil, concrete or asphalt, reflects, absorbs and emits energy differently across these wavelengths, producing characteristic spectral signatures. These signatures allow analysts to distinguish different land cover types and physical conditions. For example, healthy vegetation tends to strongly reflect near-infrared radiation and absorb red light, while built-up areas often display higher reflectance in the visible and short-wave infrared bands. Thermal infrared bands provide information on surface temperature, which is critical for assessing heat stress. The slide emphasizes that understanding which wavelengths a sensor captures, and how these relate to surface properties, is essential for selecting appropriate datasets and for correctly interpreting derived indices and classifications in urban resilience studies. Here we explain the four main types of resolution that determine the level of detail and quality of remote sensing data. Spatial resolution refers to the size of the ground area represented by a single pixel, with finer resolutions, for example, 1 to 5 meters, capturing individual buildings and narrow streets, and coarser resolutions, 10 to 30 meters or more, being more suitable for neighborhood or regional scale analysis. Spectral resolution describes how many bands a sensor records and how narrow they are, which influences the ability to distinguish between different materials and conditions. Temporal resolution relates to how often a sensor revisits the same location, a key factor for monitoring dynamic phenomena such as floods, vegetation growth, or rapidly changing urbanization fronts. Radiometric resolution, expressed in bits, indicates how finely a sensor can discriminate differences in energy, affecting the robustness of quantitative analyses. The slide stresses that there are always trade-offs. Very high spatial and spectral resolution may come with larger data volumes, higher costs or lower temporal frequency. Selecting the right resolution is therefore a strategic decision tied to the planning question, the scale of the city, available resources and the required level of detail. We discuss the main families of remote sensing sensors and their relevance for urban resilience. Passive sensors, such as optical and thermal instruments on satellites like Sentinel-2 and Landsat, measure natural radiation from the sun that is reflected or emitted by the Earth's surface. They are widely used for land cover mapping, vegetation indices, surface temperature estimation and change detection. Active sensors, such as synthetic aperture radar, SAR, and LiDAR, emit their own energy and record the backscattered signal. SAR operates in the microwave region and is largely independent of daylight and cloud cover, making it particularly valuable for flood mapping, ground deformation studies and monitoring surface roughness or moisture. LiDAR sends laser pulses and measures the return time to create detailed three-dimensional point clouds of terrain and built structures. Here we highlight that each sensor type has strengths and limitations. Optical data are intuitive and visually rich but sensitive to clouds, radar can penetrate clouds but requires more specialized interpretation, and LiDAR provides excellent 3D detail but usually covers smaller areas and is costlier. For resilient urban planning, combining these complementary sensor types often yields the most complete picture. There are different platforms that carry remote sensing sensors and they shape data availability differently. Satellite platforms provide regular, often global coverage and form the backbone of most remote sensing applications. Public missions such as Landsat and Sentinel provide freely accessible data with medium spatial resolution and long time series, ideal for analyzing urban growth, land cover change and heat island trends. Commercial satellites offer sub-meter imagery that can resolve individual buildings and street trees, which is valuable for detailed exposure analysis or informal settlement mapping, but often involves license costs. Airborne campaigns, including those flown by governmental agencies or research institutions, can carry high-resolution cameras or LiDAR to produce detailed orthophotos and digital elevation models over selected regions. Unmanned aerial vehicles, or drones, provide flexible, on-demand data collection over smaller areas, useful for specific projects such as post-disaster damage assessment or monitoring pilot nature-based solutions. Here we emphasizes that platform choice affects spatial coverage, revisit time, legal requirements and cost, and that resilient city planning frequently requires a combination of satellite and local platforms to link strategic overviews with neighborhood-scale design. This slide summarizes the main categories of remote sensing products that are directly relevant for ecological planning and disaster risk management in cities. Land use and land cover maps derived from multispectral imagery show the distribution of built-up areas, vegetation, water bodies, bare soil and other cover types, providing the foundation for calculating impervious surface ratios, fragmentation of green spaces and changes in urban form. Land surface temperature products, typically derived from thermal bands, reveal spatial patterns of heat stress and are used to quantify the intensity of urban heat islands. Vegetation indices such as NDVI or EVI quantify the presence and condition of vegetation, which can be linked to ecosystem services like cooling, carbon storage and stormwater retention. Digital elevation models, created from radar or LiDAR, describe terrain height and slope, enabling analyses of runoff, landslide susceptibility and flood pathways. Additional products include flood extent maps, soil moisture indicators and coastline or riverbank change maps. The slide emphasizes that these products are most powerful when they are not viewed in isolation but integrated with demographic, infrastructural and socio-economic information in a GIS. Here we connect remote sensing products to the widely used Hazard Exposure Vulnerability Framework derived from the Sendai Framework for Disaster Risk Reduction. Hazards, such as floods, landslides, heat waves or storm surges, can often be characterized or approximated using remote sensing data. Flood inundation can be delineated from optical or radar images, landslides can be mapped from change detection, and heat waves can be assessed through land surface temperature. Exposure deals with the presence of people, buildings and infrastructure in hazard-prone locations, for which land use maps, building footprint datasets and transport network layers derived from imagery provide critical information. Vulnerability is more complex, as it includes social, economic and institutional dimensions. However, remote sensing can provide proxies such as housing density, roof materials or the absence of vegetation and open space. We explain that combining these layers allows analysts to produce spatially explicit risk maps and to identify priority areas for intervention. We also notes that remote sensing information can support the monitoring of global agendas, such as Theo's Sendai Framework and the Sustainable Development Goals, by providing consistent indicators across cities and time. The focus here are urban heat islands, one of the most studied intersections between remote sensing and urban resilience. Urban heat islands arise because dense built-up areas with dark, impervious surfaces absorb and store more heat than vegetated or rural surroundings, leading to elevated temperatures, particularly at night. We explain that thermal infrared bands from satellites such as Landsat can be processed to estimate land surface temperature, which serves as a proxy for the spatial pattern of heat intensity across a city. When combined with land use and vegetation indices, these maps reveal which neighborhoods lack cooling green spaces or are dominated by asphalt and concrete. Such information is extremely valuable for public health planning, energy efficiency strategies and green infrastructure design. City authorities can use remote sensing-based heat maps to prioritize tree planting campaigns, park development, reflective roofing programs or shading interventions around vulnerable facilities such as schools, elderly homes and hospitals. The repeated thermal observations enable evaluation of whether implemented measures actually reduce heat intensity over time. We present flood risk as another central domain where remote sensing brings clear added value. Flood extent can be mapped directly from optical images when skies are clear by contrasting water and land using spectral indices or classifications. However, floods often occur under cloudy conditions, in which case radar imagery becomes particularly important because microwave signals penetrate clouds and can differentiate between open water and non-flooded surfaces through their backscatter patterns. When such flood extent maps are combined with digital elevation models and land use information, they provide the basis for flood susceptibility assessments and for identifying low-lying, high-risk zones. Here we highlight that remote sensing-based flood products support multiple phases of disaster management. During events they provide situational awareness for emergency response. Before events they guide land use zoning, infrastructure planning and nature-based solutions such as wetland restoration. And after events they assist in damage assessment and in evaluating the effectiveness of protective measures. The integration of remote sensing flood data with population and infrastructure datasets enables planners to design targeted interventions that reduce exposure and improve recovery capacity. The aim of here is to show how high-resolution imagery can reveal patterns of urbanization that are closely tied to social vulnerability. Informal settlements, peri-urban sprawl and unplanned expansions often develop in hazardous locations such as steep slopes, floodplains, riverbanks or areas with limited infrastructure. High-resolution optical imagery and, in some cases, LiDAR can be used to delineate building footprints, road networks and urban morphology, enabling identification of densely built, irregularly planned settlements that may lack formal services. We explain that remote sensing-based mapping of such areas, when combined with knowledge of hazard zones, allows planners to see where vulnerable populations are concentrated in high-risk environments. This supports inclusive planning strategies, such as upgrading infrastructure, enhancing drainage, providing safe access routes and, where necessary, facilitating participatory relocation. At the same time, we note the sensitivity of working with data on informal settlements and emphasizes the need for ethical guidelines and engagement with local communities when using remote sensing information that could potentially stigmatize or expose residents. We emphasizes that remote sensing becomes truly powerful when integrated with GIS and diverse non-spatial datasets. We explains that remote sensing layers, such as land cover classifications, land surface temperature, flood susceptibility indices and vegetation metrics, can be overlaid with census data, socio-economic indicators, infrastructure networks and administrative boundaries to create multi-criteria assessments. For example, a city can develop a composite heat vulnerability index that combines land surface temperature, lack of vegetation, population density, age structure and health indicators. Similarly, flood risk maps can be refined by integrating information on road networks, critical facilities and social vulnerability. Modern GIS platforms, including web-based dashboards, allow these integrated layers to be visualized, queried and shared with various stakeholders, facilitating evidence-based discussions. Here we also briefly note that artificial intelligence methods increasingly use remote sensing and GIS layers as inputs for predictive models, scenario simulations and optimization tools, which aligns closely with EPD-Net's ambition to develop AI-supported training modules for ecological planning and design. The purpose here is to encourage a critical and responsible use of remote sensing data. We point out that all data and models contain uncertainties arising from sensor noise, atmospheric conditions, misregistration, classification errors, mixed pixels and assumptions made during processing. Coarse spatial resolution may hide fine-scale heterogeneity, while infrequent temporal coverage may miss short-lived events. These uncertainties can have real consequences if risk maps are interpreted too literally, potentially leading to misallocation of resources or neglect of certain areas. We also stress that access to high-quality data and technical capacity is uneven across regions, potentially reinforcing inequalities. From an ethical perspective, mapping informal settlements, refugee camps, or other sensitive locations raises concerns about privacy, surveillance and unintended misuse of information. Here we encourage practitioners and students to document their data sources and methods transparently, to communicate uncertainty and limitations clearly in reports and maps, and to engage with local communities and decision-makers when designing analyses that could affect vulnerable groups. Here we present a small set of concise case examples that demonstrate how remote sensing has been successfully applied in urban resilience contexts. One example can describe a Mediterranean or Turkish city where Landsat-derived land surface temperature and Sentinel-2 vegetation indices were used to map urban heat islands and identify priority zones for tree planting and park creation, leading to concrete changes in municipal greening programs. A second example can focus on an urban flood risk project in which radar-based flood extent maps and digital elevation models were combined with building footprints and population data to design evacuation routes and to target investments in drainage infrastructure. A third example may highlight a pilot project where high-resolution imagery and machine learning models were used to map informal settlements and assess how their exposure to hazards could be reduced through upgrading and nature-based solutions. We emphasizes that in each case the technical analysis was closely linked to a clear policy question, that stakeholders were involved in interpreting results, and that remote sensing served as one of several evidence streams rather than as a standalone solution. We synthesize the core points of the presentation and reinforces the main messages students should retain. We reiterate that remote sensing is a powerful, scalable and increasingly accessible technology for observing cities as dynamic socio-ecological systems. By providing repeated, spatially explicit measurements of land cover, surface temperature, elevation and other variables, it enables planners to diagnose hazard patterns, track exposure and monitor the effectiveness of resilience interventions. Here we stress that understanding basic concepts such as resolutions, sensor types and data products is essential for making informed choices about which datasets to use and how to interpret them. We also highlights that remote sensing information becomes most valuable when integrated with socio-economic data and used within participatory planning processes that account for local knowledge and priorities. Finally, we remind students that a critical attitude towards data quality, uncertainty and ethics is necessary to ensure that remote sensing-based analyses genuinely contribute to more just, sustainable and disaster-resilient cities.